Welcome. In this lecture, which has multiple sessions, we'll explore linear inequality constraints. We'll mainly do this by exploring some slides, and only at the end will we get down into some details. The main concepts for this lecture are that a linear inequality is this. It's a matrix times a vector, and that's less than or equal to a constraint vector. Previously, it had to be equal. Now we're saying it's less than or equal. And that means that linear inequalities are a convex set. Linear equalities, you could think of, were level curves, and now we're looking at level sets. A feasible point is one that satisfies every possible inequality constraint that is provided. And the KKT conditions are what the lecture will end with, and these are necessary and sufficient for linear inequalities. Along the way, we can think about a vector being of minimum length and still being inside a set of linear boundaries. So let's take a simple example with size 2 vectors. Suppose that we have 4 constraints. One is that the first entry has to be non-negative. The second constraint is that the second entry has to be non-negative. The third constraint is that the first entry has to be less than or equal to 3. And then we want the sum of the entries to be less than or equal to 4. We can use simple graphs to understand these. So the first one is saying that the feasible set is the set of all vectors whose first entry is greater than or equal to 0. So this shaded portion indicates the feasible part of that constraint. The second is saying that the second constraint is saying that the second entry of the vector has to be non-negative. The third is saying that the first entry has to be less than or equal to 3, and the fourth constraint is that the sum of them has to be less than or equal to 4. So that's inside that shaded area. When we combine these, each of these constraints is a convex set, and that means that their intersection is a convex set. And in this case, the intersection is a quadrilateral. So there were 4 constraints. Those are providing 4 boundaries, and those 4 boundaries are describing a convex set. Depending on your constraints, it might not necessarily look like this. It might, for example, be describing part of a plane. That is, part of this might go to infinity. So the feasible set that we'll be looking at is, in this case, the intersection of all 4 constraints. Now, suppose that we have an objective function. Here, I'm picking a very simple objective function. So this is just the squared norm of the distance from a vector to a reference point. The problem for constrained optimization is which point inside this shaded quadrilateral is closest to that reference point. And that is a convex optimization problem with linear inequality constraints. In this case, we calculate that to be the point in the feasible set that's closest to this reference point, and that reference point has a first entry of 3 and a second entry of 2. So that's the sort of problem that we're looking at, and we can go through these by hand, and we will later on, but for now, we'll just try to appreciate them graphically.